morning of September 5th, 1977, NASA launched a spacecraft called Voyager One. It was supposed to be a 4-year mission to photograph Jupiter and Saturn. But the little probe just kept going and going and going. Today, nearly 50 years later, Voyager One is the most distant human-made object in existence. It has traveled over 167 times the distance from Earth to the Sun. It is moving at 17 kilometers per second, which is about 38,000 miles per hour. At that speed, you could fly from New York to Los Angeles in under 4 minutes. Voyager One has left the solar system. At least, that is what the headline said when it crossed the heliopause in 2012. It has entered interstellar space. Mission accomplished, right? Not even close. Because here is the thing nobody tells you. Voyager One has not actually left the solar system. Not really. It has barely scratched the surface of what our sun calls home. The true edge of the solar system is so impossibly far away that Voyager One, traveling at 38,000 miles per hour, will need another 30,000 years to reach it. 30,000 years. That is longer than human civilization has existed. That is roughly how long ago we were still painting on cave walls. And what lies between Voyager and the true edge of the solar system? A place so vast, so empty, and so bizarre that most people have never even heard of it. It is called the Oort Cloud, and its scale is gonna break your brain. Let me give you the number first, and then I will spend the rest of this video helping you actually understand what it means. The Oort Cloud extends up to 100,000 astronomical units from the Sun. Some estimates say 200,000. An astronomical unit is the distance from Earth to the Sun, about 93 million miles. So we are talking about a structure that extends up to 200,000 times farther from the Sun than Earth does. In more familiar terms, that is roughly 1.5 to 3 light years across. The nearest star to our Sun, Proxima Centauri, is 4.2 light years away. The Oort Cloud extends halfway to the nearest star. Let that sink in for a moment. There is a part of our solar system, a structure that belongs to our Sun, that reaches almost halfway to another star. When astronomers draw diagrams of the solar system, they usually show the planets, maybe the asteroid belt, sometimes the Kuiper belt out past Neptune. But they almost never show the Oort Cloud, because if they drew it to scale, it would not fit on any page. It would not fit on a billboard. It would not fit on the side of a building. If you drew the solar system with Earth 1 inch from the Sun, the Oort Cloud's outer edge would be more than 3 miles away. This is not some minor feature of our cosmic neighborhood. The Oort Cloud is the solar system. Everything else, all 8 planets, all the moons, all the asteroids and comets you have ever heard of, they are just a tiny bright dot at the center of something almost incomprehensibly vast. And yet, despite containing an estimated 1 trillion objects, despite spanning more than a light year in every direction, despite being the largest structure associated with our Sun, the Oort Cloud has never been directly observed, not once. No telescope has ever photographed an Oort Cloud object. No spacecraft has ever visited one. We know it exists because of math, because of detective work, because a Dutch astronomer in 1950 looked at the orbits of a handful of comets and deduced that something extraordinary must be lurking in the darkness. This is the story of the Oort Cloud, the solar system's final frontier, the ghost at the edge of everything we know. But first, let me make sure you actually understand just how far away we are talking about. Because the numbers I just gave you, they do not mean anything yet. Your brain cannot process distances this large. Nobody's can. So let me try some comparisons. You know how long it takes light to travel from the sun to Earth? 8 minutes. Light moves at 671 million miles per hour, and it still takes 8 minutes to cover the distance between us and the sun. How long does it take that same light to reach Neptune, the most distant planet? About 4.5 hours. How long to reach the Kuiper Belt, that ring of icy objects beyond Neptune where Pluto lives? Maybe 5 or 6 hours. How long to reach the heliopause, the boundary that Voyager One crossed in 2012? About 17 hours. How long to reach the inner edge of the Oort Cloud? Between 10 and 28 days. And how long to reach the outer edge? Up to 1.5 years. Light itself, the fastest thing in the universe, needs up to 18 months to cross from the sun to the outer boundary of the Oort Cloud. When you look up at the stars tonight, the photons hitting your eyes left those stars years or decades or centuries ago. But light from the outer Oort Cloud, if there were any to see, would have left sometime last year. This is a deeply strange thought. We are used to thinking of our solar system as something immediate, something local. The sun warms our faces in real time. The moon's light reaches us in just over a second. Even the outer planets, though far away, feel close enough to understand. But the Oort Cloud breaks that intuition. If something dramatic happened at the outer edge of the Oort Cloud right now, we would not know about it for 18 months. The information about that event, traveling at the speed of light, would take 1.5 years to reach us. The Oort Cloud is so large that it introduces light delay within our own solar system, comparable to the delays we experience communicating with distant spacecraft. When New Horizons flew past Pluto in 2015, the signal took about 4.5 hours to reach Earth. Communications with Voyager One currently take about 23 hours each way. But if we could somehow communicate with something at the outer edge of the Oort Cloud, the round-trip signal time would be 3 years. Any conversation would span years between question and answer. Still not clicking. Let me try something else. Let us talk about Voyager One again. Right now, as I am saying these words, Voyager is about 167 astronomical units from the Sun. It has been traveling for nearly 50 years. It is moving faster than any human has ever traveled, faster than any bullet, faster than most things you can imagine. The inner edge of the Oort Cloud is at least 2,000 astronomical units away. At its current speed, Voyager One will reach the inner edge of the Oort Cloud in approximately 300 years, around the year 2300, give or take. And how long until Voyager crosses the entire Oort Cloud and exits the other side? 30,000 years, maybe longer. By the time Voyager One leaves the true solar system, human civilization will either be unrecognizable or extinct. The Egyptian pyramids were built about 5,000 years ago. Voyager's journey through the Oort Cloud will take 6 times longer than the entire history of ancient Egypt. The domestication of dogs happened about 15,000 years ago. Voyager's journey will take twice that long. We measure our history in centuries. We measure the Oort Cloud in tens of millennia. The The scale is fundamentally different from anything we normally think about. And here is the kicker. Voyager One will almost certainly never hit anything. Despite the Oort Cloud containing roughly 1 trillion objects, it is so unimaginably vast that those objects are separated by tens of millions of kilometers on average. Voyager could travel through the entire cloud for 30,000 years and never come within 10 million kilometers of a single chunk of ice. The Oort Cloud is simultaneously the most crowded region of the outer solar system and the emptiest place you can imagine. Okay, I have thrown a lot of numbers at you. Let me try one more comparison, and then we will move on to something more interesting. Imagine you shrunk the entire solar system down so that the sun was the size of a basketball. At this scale, Earth would be a small peppercorn about 26 meters away. Neptune, the outermost planet, would be almost a kilometer from the basketball sun. Where would the Oort Cloud be? Its inner edge would start roughly 2 kilometers from the basketball, not 2 kilometers across, 2 kilometers away, and its outer edge about 100 kilometers away from that basketball. Farther than a marathon, farther than most people drive in a day, and somewhere in that vast sphere, 100 kilometers in radius, with the entire known solar system crammed into the first kilometer, there are 1 trillion chunks of ice drifting through absolute darkness. That is the Oort Cloud. Now let me tell you how we know any of this, because remember, no one has ever seen it. No one has ever photographed it. No one has ever sent a probe there. So how can astronomers be so confident that this enormous invisible shell actually exists? The answer begins with comets. For centuries, humans have watched comets streak across the sky. They were omens, portents, signs from the gods. Ancient cultures believed comets predicted the deaths of kings, the fall of empires, plagues, and disasters. The word comet itself comes from the Greek word for long-haired, a reference to their distinctive tails streaming across the night sky. The ancient Greeks debated what comets were. Aristotle believed they were atmospheric phenomena, disturbances in the upper air, not true celestial objects. This view persisted for nearly 2,000 years. It was not until Tycho Brahe carefully measured the position of the Great Comet of 1577 from multiple locations that astronomers proved comets were farther away than the Moon, true members of the solar system. Edmund Halley was the first to realize that comets followed predictable orbits. Studying historical records, he noticed that bright comets had appeared in 1682, 1607, and 1531, roughly 75 to 76 years apart. He proposed that these were all the same comet, returning on a regular schedule, and he predicted it would return again in 1758. Halley died in 1742, but his prediction came true. The comet appeared on Christmas night, 1758, and was named in his honor. It was the first time anyone had successfully predicted a comet's return. But as astronomy matured, scientists began to study their orbits more carefully, and they noticed something strange. Some comets, like Halley's comet, return on predictable schedules. Halley shows up every 76 years or so, swooping in from just beyond Neptune's orbit. These short-period comets made sense. They were clearly members of the solar system, trapped in elliptical orbits around the sun. But other comets were different. They came from nowhere, plunging into the inner solar system from random directions, looping around the Sun once and then vanishing back into the void. Their orbital periods were not decades, they were thousands of years, tens of thousands of years. Some would not return for millions of years, if ever. And there was another problem. Comets could not be eternal. Every time a comet passes close to the Sun, it loses mass. The ice sublimates into gas, the dust blows away, and the comet gets smaller. After enough passes, there should be nothing left. If comets had been orbiting the Sun since the solar system formed 4.5 billion years ago, they should all have evaporated long ago. Yet new comets kept appearing. Fresh comets, with pristine surfaces that had clearly never been heated by the Sun before. Where were they coming from? Where were these long-period comets originating? And why did they arrive from every direction, above and below the plane of the planets, rather than from the flat disk where everything else orbited? This mystery haunted astronomers for generations. Everyone knew comets came from somewhere, but no one could explain where fresh comets kept coming from, or why they arrived from such random directions. In 1932, an Estonian astronomer named Ernst Öpik proposed an answer. He suggested that long-period comets originated in a vast cloud of icy objects at the very edge of the solar system. Occasionally, the gravity of passing stars would nudge one of these objects, sending it falling inward toward the Sun. We would see it as a comet, a brief visitor from the depths. Öpik was a remarkable scientist in his own right. Born in Estonia in 1893, he made significant contributions to the study of meteors, asteroids, and stellar evolution. He correctly estimated the distance to the Andromeda Galaxy in 1922, long before Edwin Hubble's more famous measurement. He even predicted the existence of oceans on Europa, Jupiter's moon, decades before Voyager confirmed it. But Öpik's paper on the comet cloud was published in a relatively obscure journal and did not attract widespread attention. The idea was noted and largely set aside. Sometimes scientific ideas arrive before the world is ready for them. 18 years later, a Dutch astronomer named Jan Oort independently arrived at the same conclusion, but with something Öpik had lacked: mathematical proof. Oort was born in the Netherlands in 1900, and by the time he turned his attention to comets, he was already one of the most respected astronomers in the world. In 1927, at just 27 years old, he had confirmed that the Milky Way galaxy rotates, and he calculated the rotation curve that bears his name. The Oort constants are still used today to describe galactic rotation. In 1950, Oort published a landmark paper titled "The Structure of the Cloud of Comets Surrounding the Solar System and a Hypothesis Concerning Its Origin." He had analyzed the orbits of 19 long-period comets, carefully computing where they must have originated. And he discovered something remarkable. 10 of these comets were fresh, first-time visitors to the inner solar system. They had pristine surfaces that had never been heated by the Sun before, and they all came from approximately the same distance. Their farthest points from the Sun, their aphelia, clustered around 20,000 astronomical units. Later work by astronomer Brian Marsden refined this clustering to about 40,000 to 50,000 astronomical units. But the key insight remained. The clustering was not random. It was a fingerprint. Something was out there at that specific distance, a reservoir of potential comets waiting to be disturbed. Even more tellingly, these long-period comets arrive from all directions, not from the flat ecliptic plane where the planets orbit, but from above, below, and everywhere in between. Whatever was sending them had to be spherical, surrounding the entire solar system like a shell. Oort had discovered the cloud that would bear his name. But wait, why does Oort get the credit when Öpik proposed the idea first? Mostly because Oort's paper was more rigorous, more mathematical, more convincing to the scientific community. He did not just suggest the cloud existed. He showed exactly why it must exist, backed by careful orbital calculations. Öpik had the intuition. Oort had the proof. Oort was also more prominent in the astronomical community. He went on to become president of the International Astronomical Union. He pioneered radio astronomy and made fundamental contributions to our understanding of the Milky Way galaxy. His team was the first to detect the 21-centimeter hydrogen emission line that is now fundamental to mapping the structure of galaxies. He even helped discover evidence for dark matter, recognizing that the visible matter in the galaxy could not account for its rotation. Jan Oort lived to be 92 years old, dying in 1992. He spent his entire career transforming our understanding of the cosmos, and today, his name is attached to a structure that no one has ever actually seen. Some astronomers use the term Oort Cloud to acknowledge both contributions, but in common usage, it is simply the Oort Cloud. And for 75 years now, every long-period comet that has plunged through the inner solar system has reinforced Oort's hypothesis. The math keeps working, the fingerprint keeps appearing. The cloud is real, even if we cannot see it. So what exactly is out there? What is the Oort cloud made of? Imagine 1 trillion snowballs. Some are a few meters across. Some are the size of mountains. Most are smaller than 100 kilometers in diameter, dark, frozen, and ancient. They have been drifting in the darkness for 4.5 billion years, since the solar system was young. These objects are made of ice, but not just water ice. They contain frozen methane, ammonia, carbon monoxide, carbon dioxide, ethane, and hydrogen cyanide. They are the primordial building blocks of the solar system, preserved in a deep freeze just a few degrees above absolute zero. The temperature out there hovers around 4 to 5 Kelvin. Let me put that in perspective. That is negative 450 degrees Fahrenheit. Colder than any place on Earth has ever been. Colder than liquid nitrogen. Colder than anywhere you have ever experienced or could ever experience without dying instantly. At those temperatures, nothing changes, nothing melts, nothing evaporates, nothing decays. The icy objects in the Oort cloud have been in essentially the same state for 4.5 billion years. They are time capsules from the birth of the solar system, preserved more perfectly than any artifact on Earth. When a comet falls inward from the Oort cloud and approaches the sun, those ancient ices begin to sublimate, turning directly from solid to gas in the vacuum of space. The gas carries dust with it, forming the fuzzy coma around the nucleus and the long tail that streams away from the sun. That tail is not exhaust trailing behind the comet like smoke from a rocket. It always points away from the sun, pushed by solar radiation and the solar wind. Different ices sublimate at different distances. Carbon monoxide starts vaporizing when a comet is still beyond Saturn's orbit. water ice does not start sublimating significantly until the comet is within about 3 astronomical units of the Sun, roughly the distance of the asteroid belt. By analyzing the composition of comet tails and comas, we can determine what the original object was made of. And this tells us something profound about the early solar system. The ices in Oort Cloud comets contain the same ratios of certain isotopes as the ices found in molecular clouds, the cold, dense regions of space where stars form. This suggests that some of the material in Oort Cloud objects predates the solar system itself. It was inherited directly from the cloud of gas and dust that collapsed to form our Sun 4.5 billion years ago. Think about that. When you look at a comet, you might be looking at material that is older than the Sun, material that drifted through interstellar space for millions of years before being incorporated into the solar nebula. These are among the oldest, most pristine objects in existence. In 2004, NASA's Stardust mission collected samples from the coma of Comet Wild 2 and returned them to Earth. Analysis of those samples revealed amino acids, the building blocks of proteins, and other complex organic molecules. This added support to an idea that had been floating around for decades. Comets may have delivered some of the raw materials for life to the early Earth. The Stardust mission was remarkable. A spacecraft flew through the coma of a comet, captured tiny particles of dust and ice in a special material called aerogel, and brought them back to Earth. It was the first sample return mission from beyond the Moon. What scientists found was astonishing. Glycine, one of the amino acids used by all life on Earth, was present in the samples. So were other complex organic molecules, hydrocarbons and nitriles, that could serve as building blocks for more complex chemistry. This does not prove that life on Earth came from comets, but it strongly suggests that comets contributed to the primordial soup from which life emerged. Here is the scenario many scientists now consider plausible. 4 billion years ago, the inner solar system was being pummeled by debris left over from planetary formation. This period, called the Late Heavy Bombardment, saw countless asteroids and comets striking the young Earth. Many of those impacts were catastrophic, sterilizing the surface with each strike. But some of those impacts delivered water. The Earth's oceans may owe their existence, at least in part, to comet impacts. The ratio of hydrogen isotopes in Earth's water is still being studied to determine exactly what fraction came from comets versus asteroids, but comets were definitely contributors. And with that water came organic molecules, amino acids, sugars, the raw materials from which living cells are built. The Oort Cloud, in this view, was not just a distant curiosity. It was a vast warehouse of prebiotic chemistry, material that seeded the young Earth with the ingredients for life. Every time a comet from the Oort Cloud struck the early Earth, it delivered a package of complex molecules that had been assembling in interstellar space for millions of years before our solar system even formed. In 2020, scientists announced that they had found phosphorus and fluorine in the coma of Comet 67 P. Churyumov-Gerasimenko, studied by the Rosetta mission. Phosphorus is a key element in DNA and in ATP, the energy currency of all living cells. Its presence in comets strengthens the case that comets provided essential ingredients for life. The Rosetta mission was one of the most ambitious comet studies ever attempted. Launched by the European Space Agency in 2004, it chased Comet 67P for 10 years before finally catching up with it in 2014. It then orbited the comet for 2 years, studying it in unprecedented detail. Rosetta even deployed a lander called Philae onto the comet's surface. The landing did not go as planned. Philae bounced twice before settling in a shadowed area where its solar panels could not charge properly. But before its batteries died, Philae sent back invaluable data about the comet's composition and structure. What Rosetta found was remarkable. The comet was not a single solid object, but a contact binary, 2 lobes stuck together, looking somewhat like a rubber duck. Its surface was covered with dust and organic compounds. Its interior was porous, more like a sponge than a solid rock. And the ice inside contained molecular oxygen, which was completely unexpected. Scientists had assumed that oxygen would have reacted with hydrogen to form water long ago. Its presence suggested that the comet had been formed in extremely cold conditions and had never been significantly heated. This is the kind of thing we can learn from comets. Each one is a messenger from the Oort Cloud, carrying information about conditions that existed billions of years ago. The more closely we study them, the more we learn about the early solar system and the origins of life. Water on Earth might have come from comets. Organic molecules on Earth might have come from comets. The Oort Cloud, in a very real sense, might be one of the reasons we exist. There is a profound irony here. The same objects that may have helped life get started could also destroy it. Comet impacts can trigger mass extinctions. The Oort Cloud giveth, and the Oort Cloud taketh away. And yet, despite the cloud's importance, despite its size, despite containing 1 trillion objects, the Oort Cloud is overwhelmingly empty space. Here is the math. 1 trillion objects sounds like a lot, and it is, but spread across a sphere that extends up to 100,000 astronomical units in radius, those trillion objects become incredibly sparse. On average, neighboring Oort Cloud objects are separated by about 50 million kilometers. That is roughly a third of the distance from Earth to the Sun. That is comparable to the closest approach distance between Earth and Mars. If you were randomly placed somewhere in the outer Oort Cloud, you would see nothing. Absolutely nothing. The nearest chunk of ice would be tens of millions of kilometers away, far too small and dark to reflect any detectable light. Your eyes would register only stars, the same stars you would see from Earth, with no indication that you were inside anything at all. The Oort Cloud bears no resemblance to the asteroid field in The Empire Strikes Back. It is not a crowded swarm of rocks that you need to dodge. It is emptiness on a scale that defies description, punctuated by occasional specks of ice so widely spaced that you could travel for years without coming close to one. Now here is something that might surprise you. These objects did not form where they currently reside. The Oort Cloud is not where these icy bodies were born. It is where they were exiled 4.5 billion years ago, when the solar system was still forming. These chunks of ice were much closer to the Sun. They formed in the region between 15 and 35 astronomical units, roughly where Uranus and Neptune orbit today. They were icy planetesimals, the building blocks that could have become planets or moons if they had been luckier. But they were not lucky. They got too close to the giant planets. Jupiter, Saturn, Uranus, and Neptune were growing rapidly, their gravity intensifying. Any small body that wandered too close got flung outward like a rock from a slingshot. Most were ejected from the solar system entirely, cast into interstellar space to drift forever between the stars. This process was chaotic and violent. The early solar system was nothing like the orderly arrangement we see today. The giant planets were closer to the Sun and closer to each other. They jostled for position, their orbits shifting over millions of years. According to a model called the Nice model, named after the city in France where it was developed, there was a dramatic period of instability roughly 4 billion years ago. Jupiter and Saturn fell into a gravitational resonance, their orbital periods briefly synchronizing in a way that destabilized the entire outer solar system. Neptune may have been flung outward, plowing through a dense disk of icy planetesimals that existed beyond the original positions of the giant planets. This event scattered trillions of objects. Some were sent into the inner solar system, causing the late heavy bombardment that cratered the moon and the inner planets. Some were ejected into interstellar space, and some were scattered into what would become the Oort Cloud. But some objects got lucky in a different way. These objects were thrown outward, but not quite hard enough to escape. They reached enormous distances from the Sun, thousands or tens of thousands of astronomical units, and then their orbits carried them back inward. They should have returned to the inner solar system, perhaps to be flung out again or finally ejected for good. But at those extreme distances, other forces intervened. The Milky Way galaxy itself has gravity. It is subtle, spread across billions of stars and countless light years, but it is there. And at Oort Cloud distances, where the Sun's gravity is extraordinarily weak, galactic tides start to matter. These galactic tides gently lift the perihelion, the closest approach point, of distant objects, pulling them away from the dangerous region near the giant planets. Once their perihelia were raised, these objects were trapped. They could no longer return to the inner solar system. They were stuck in the Oort Cloud, circling the Sun on million-year orbits, slowly randomizing their orientations until they formed a spherical shell surrounding everything. This is why the Oort Cloud is spherical, while the Kuiper Belt and Asteroid Belt are flat disks. The Kuiper Belt objects never left the plane of the solar system. They formed in place, or were only mildly scattered, retaining their original alignment with the planets. But Oort Cloud objects were violently ejected in random directions, and then galactic tides randomized their orbits even further. Only about 3 to 5% of the original scattered planetesimals ended up in the Oort Cloud. The vast majority escaped into interstellar space. Jupiter and Saturn were actually bad at populating the cloud because their gravity was too strong. They ejected objects too violently, giving them enough velocity to escape the Sun's gravity entirely. Uranus and Neptune, with their weaker gravity and wider orbits, were more efficient at the soft ejection process that allowed galactic forces to capture objects before they escaped. The Oort Cloud is a cosmic prison, or maybe a cosmic retirement home. Trillions of ancient icy bodies, the rejects and refugees of planetary formation, spending eternity in the darkness. And here is something even more remarkable. The Sun probably did not form alone. Current models suggest the Sun was born in a cluster of 200 to 400 stars. And that cluster stayed together for millions of years before dispersing. During that time, stellar encounters were far more frequent than they are today. Some researchers believe that up to 90% of Oort Cloud comets may have originated in the protoplanetary disks of other stars in the Sun's birth cluster. These objects were captured as the cluster dispersed, stolen from our stellar siblings before they drifted apart. If that is true, then when we look at a comet, we might not be looking at material from our own solar system at all. We might be looking at a visitor from another star, captured 4 billion years ago and waiting in the darkness ever since. And every once in a while, one of these ancient exiles gets paroled. When a passing star or giant molecular cloud drifts near enough to the solar system, its gravity can perturb Oort Cloud objects. Not dramatically, not violently, but enough. An orbit that was stable for 1 billion years suddenly is not. The object's perihelion drops. It begins falling inward, picking up speed as it goes, until eventually it screams through the inner solar system, grows a tail of vaporizing ice, and becomes what we call a comet. This is where the great comets come from. Not the Kuiper belt, not the asteroid belt, the Oort Cloud. Let me tell you about some of the most spectacular ones. Comet Hale-Bopp appeared in 1996 and 1997 and became one of the most spectacular comets of the 20th century. It was visible to the naked eye for 18 months straight, a record. If you were alive in 1997 and looked up at the night sky at any point, you probably remember it. Its nucleus was about 60 kilometers across, 6 times larger than Halley's Comet. Scientists believe Hale-Bopp formed 4 billion years ago, somewhere between Jupiter and Neptune, and was flung outward into the Oort Cloud during the chaotic early days of the solar system. For billions of years, it sat out there in the darkness, frozen, undisturbed. Then something nudged it, maybe a passing star, maybe the subtle gravitational tug of the Milky Way itself. Whatever it was, Hale-Bopp began its long fall inward. Its orbital period is about 2,500 years. The last time Hale-Bopp visited the inner solar system, the ancient Greeks were building the Parthenon. The next time it returns, human civilization will be completely unrecognizable, if it exists at all. Comet Hyakutake appeared in 1996, just a year before Hale-Bopp. It passed within about 10 million miles of Earth, one of the closest comet approaches in 200 years. Its tail stretched nearly 100 degrees across the sky. It was the first comet ever observed emitting X-rays. Here is the mind-bending part. Hyakutake's orbital period before that visit was about 17,000 years. The last time it swung through the inner solar system, modern humans were in the Stone Age. We had not invented agriculture. We had not domesticated animals. The last ice age was still in full swing. And because of gravitational perturbations during its 1996 passage, Hyakutake's new orbital period is roughly 70,000 years. The next time it returns, humanity might not exist anymore. Whatever species is walking the Earth in 70,000 years, assuming anything is, will see a comet that we saw, visiting from the same ancient source. Then there was the Great Comet of 1811. It remained visible to the naked eye for 260 days, a record that stood until Hale-Bopp. Its coma was approximately 1 million miles across, 50% larger than the Sun itself. Napoleon associated it with his invasion of Russia. Winemakers called 1811 the Comet wine vintage, believing the comet had blessed their grapes. The Great Comet of 1811 will not return for about 3,000 years. The world it returns to will be nothing like the world that watched it last time. These are not just beautiful lights in the sky. They are messengers from the edge of everything. Each one carries information about conditions 4.5 billion years ago, frozen in ice and preserved in the darkness. When we study comets, we are studying the birth of the solar system itself. I need to mention something important here. Halley's Comet, probably the most famous comet in history, is not from the Oort Cloud. Its orbital period is only 76 years. Its aphelion, its farthest point from the Sun, is just about 35 astronomical units, barely beyond Neptune. Halley's Comet is what astronomers call a short-period comet, and it almost certainly originated in the Kuiper Belt, not the Oort Cloud. The distinction matters. Kuiper Belt comets orbit in the plane of the planets and return frequently. Oort Cloud comets come from all directions and may take millions of years between visits. They are fundamentally different populations with different origins and different histories. If someone tells you Halley's Comet is from the Oort Cloud, they are wrong. Let me give you another famous example to drive this home. The Great Comet of 1811 was one of the most spectacular comets ever recorded. It remained visible to the naked eye for 260 days, a record that stood until Hale-Bopp nearly 2 centuries later. Its coma, the fuzzy cloud of gas and dust surrounding the nucleus, was approximately 1 million miles across. That is 50% larger than the diameter of the Sun itself. The Great Comet of 1811 appeared during a momentous year in the world history. Napoleon was preparing to invade Russia. The United States was about to fight Britain in the War of 1812, and hanging in the sky, visible for nearly 9 months, was this extraordinary celestial visitor. The comet became associated with all sorts of events. The 1811 wine vintage in Europe was exceptionally good, and winemakers called it the Comet wine or Comet vintage. People believed the comet had somehow blessed the grapes. In reality, it was just a coincidence of good weather and timing, but the legend persisted. The Great Comet's orbital period is approximately 3,000 years. It last visited around 900 BC during the Iron Age, when the Phoenicians were developing their alphabet and the Kingdom of Israel was at its height under Solomon. It will return around the year 4800 AD. What was the Great Comet doing during all that time? Falling outward toward the Oort Cloud, reaching aphelion somewhere in the distant reaches of the solar system, then beginning its long fall back inward. For 3,000 years, it traveled through darkness, invisible, unchanged, while entire civilizations rose and fell on Earth. That is what long-period comets are. Time travelers, messengers from ages so remote that they make human history seem like a brief flicker. Let me tell you about one more comet, because this one has an interesting story. Comet West appeared in 1976, just a few months after Comet Kohoutek in 1973. Kohoutek had been heavily hyped as the comet of the century. Scientists predicted it would be spectacular, bright enough to see in daylight. The media went wild. And then Kohoutek turned out to be a dud. It was visible, but not particularly impressive. The public felt disappointed, even betrayed. So when Comet West came along in '76, the scientific community and the media were gun-shy. They deliberately downplayed expectations. They did not want another Kohoutek situation. And then, Comet West turned out to be genuinely spectacular. One of the brightest comets of the 20th century. Its nucleus fragmented into 4 pieces as it rounded the sun, creating a beautiful multiple tail structure. Amateur astronomers who knew to look for it were treated to an incredible sight. But because the media had not covered it, most of the public never knew. Comet West came and went without fanfare, seen mainly by dedicated sky watchers who were paying attention. The lesson here is that comets are unpredictable. We still cannot accurately forecast how bright a comet will become or how spectacular it will be. The interplay between the comet's composition, the sun's heat, and the comet's structural integrity is too complex. Some comets exceed expectations, others fall short. But every long-period comet, whether it fizzles or dazzles, originated in the same place, the Oort Cloud. Now let me talk about what actually causes an Oort Cloud object to leave its ancient orbit and fall toward the sun. I mentioned perturbations earlier. Let me explain what that actually means. The Oort Cloud is incredibly far from the sun. At those distances, the sun's gravity is extremely weak. An object at 50,000 astronomical units is only loosely bound to the solar system. It would not take much to change its orbit. 2 main forces provide that change. The first is galactic tides. Just as the moon's gravity creates ocean tides on Earth, the gravity of the entire Milky Way galaxy exerts a subtle pull on objects in the Oort Cloud. This is not a sudden yank. It is an incredibly slow, gentle influence that accumulates over millions of years. But given enough time, it can shift an object's orbit just enough to send it falling inward. Galactic tides are responsible for up to 90% of all long-period comets. They are the primary mechanism that feeds fresh comets into the inner solar system. The second mechanism is passing stars. The sun is not stationary. It orbits the center of the Milky Way, and as it does, other stars occasionally pass nearby. Not close in human terms. We are talking about distances of light years, but close enough and massive enough to gravitationally disturb the Oort Cloud. This has happened before, and it will happen again. About 70,000 years ago, a small binary star system passed through the outer Oort Cloud itself. It came within about 52,000 astronomical units of the Sun, well inside the cloud's outer boundary. This star is called Schultz's star. It is a red dwarf paired with a brown dwarf, both very dim. Even at its closest approach, it would have been invisible to the naked eye for anyone on Earth. Modern humans existed at the time, but we were still in the early stages of migrating out of Africa. We had no idea a star was passing through our cosmic backyard, but its passage left a mark. A 2018 study found subtle signatures in the orbits of some distant solar system bodies that may be the gravitational fingerprint of Schultz's star. The perturbation was real. Comets were nudged. But here is the thing. Schultz's star moved quickly and was relatively small. Any comets it disturbed probably have not arrived yet. Their orbital periods are measured in millions of years. They might not reach the inner solar system for another 2 million years. Our distant descendants might see comet showers that were set in motion before human civilization even existed. Comets that were knocked loose from their stable orbits when our ancestors were painting on cave walls will arrive in the inner solar system when our descendants are doing things we cannot even imagine. This is one of the strangest aspects of the Oort Cloud. Cause and effect are separated by millions of years. A star passes through. Comets are disturbed, but the consequences of that disturbance will not be felt for eons. By the time the perturbed comets arrive, the star that disturbed them has long since vanished into the darkness. The connection between trigger and result is invisible to any single civilization. Now let me tell you about the next close encounter, because this one is going to be much more dramatic. There is a star called Gliese 710. It is an orange K-type dwarf, about 60% the mass of the Sun, currently about 62 light-years away in the constellation Serpens. Right now, it is completely unremarkable, just another dim star among billions. In approximately 1.3 million years, Gliese 710 will pass within about 10,500 astronomical units of the Sun. That is deep inside the outer Oort Cloud, much closer than Schultz's star came, and Gliese 710 is much more massive. Astronomers have called this potentially the strongest disrupting encounter in the future and history of the solar system. Think about that. In all the billions of years that the solar system has existed and will exist, this might be the most significant gravitational disturbance of the Oort Cloud ever. The effects will be profound. Gliese 710 is predicted to throw approximately 2.4 million new comets onto Earth crossing orbits. These comets will not arrive all at once, of course. They will trickle in over the following few million years, representing a 50% increase in long-period comet activity. At its closest approach, Gliese 710 will be the brightest star in Earth's sky, outshining even Sirius. It will appear at about magnitude -2.7, brighter than Jupiter. If there are any observers on Earth in 1.3 million years, they will see something remarkable. And then, slowly, Gliese 710 will drift away, leaving behind a gravitationally stirred Oort Cloud and an inner solar system, peppered with new comets. But Gliese 710 and Schultz's star are not unique events. They are examples of something that happens regularly over astronomical timescales. The Sun has experienced thousands of stellar encounters throughout its history and will experience thousands more using data from the Gaia Space Telescope, which has measured the positions and velocities of over 1 billion stars with unprecedented precision. Astronomers have identified dozens of stars that have passed or will pass within a few light years of the Sun. A star called HIP 85605, a small orange dwarf, passed within about 0.25 light years of the Sun, roughly 300,000 years ago. That is well inside the outer Oort Cloud. Around the same time, Gliese 710 makes its close approach. Another star called AC plus 79, 3888, will also pass within roughly a light year. Go further into the past, and the encounters get harder to track because orbital uncertainties accumulate over millions of years. But we can be confident that close stellar passages have happened many times, and each one stirred the Oort Cloud like a spoon through a bowl of soup. The Sun orbits the center of the Milky Way galaxy once every 250 million years or so. During that time, it experiences countless stellar encounters. Some are distant, barely noticeable, Others are close enough to significantly perturb the Oort cloud. The average time between close encounters, meaning stars passing within 1 or 2 light years, is probably on the order of 100,000 years or so. Over the 4.5 billion years since the Oort cloud formed, the Sun has experienced tens of thousands of these close encounters. Each one has stirred the cloud slightly. Each one has knocked a few comets onto new trajectories. The cumulative effect of all these perturbations has gradually depleted the cloud, sending material into the inner solar system or ejecting it into interstellar space entirely. The Oort cloud we have today is probably much smaller than the Oort cloud that existed when the solar system was young. Some estimates suggest we have lost 99% of the original population. What remains is the hardy remnant, the objects that happen to be in stable enough orbits to survive 4.5 billion years of gravitational stirring. This raises an uncomfortable question. Is there a connection between comet showers and mass extinctions? The hypothesis has been around for decades, and it is genuinely controversial. Here's the argument. Researchers have noticed a possible periodicity in both impact crater ages and extinction events, somewhere between 26 and 30 million years. This roughly corresponds to the time it takes for the Sun to oscillate vertically through the plane of the Milky Way as it orbits the galactic center. Think about it like this. The Milky Way is a flat disk of stars, gas, and dust. The Sun orbits the center of the galaxy, but it does not stay perfectly in the plane. It bobs up and down like a horse on a carousel, crossing the galactic midplane roughly every 30 million years. The idea is that when the Sun passes through the densest parts of the galactic plane, gravitational perturbations on the Oort cloud increase, sending more comets inward, increasing the chance of a catastrophic impact on Earth. 6 mass extinctions over the past 260 million years do seem to correlate with periods of enhanced cratering. The most famous one, the asteroid impact that killed the dinosaurs 65 million years ago, may have been part of such a shower. Some researchers have gone further. They have proposed that the impactor that killed the dinosaurs was not an asteroid at all, but a comet from the Oort cloud, knocked loose by galactic tides or a passing star, a chunk of ancient ice that had been drifting in darkness for billions of years, finally falling sunward with catastrophic results. The Chicxulub impact, as it is now known, was caused by an object roughly 10 kilometers across. Whether that object was an asteroid from the inner solar system or a comet from the Oort cloud is still debated. The crater itself does not clearly distinguish between the two possibilities, but the timing is suggestive. The impact occurred during a period when other large craters were also being formed, which could indicate a comet shower. If this hypothesis is correct, then the Oort cloud has directly shaped the history of life on Earth. The dinosaurs ruled the planet for over 150 million years. They might still be here, if not for a chunk of ice that was knocked out of the Oort cloud by some distant gravitational perturbation millions of years earlier. Their extinction opened the ecological niches that allowed mammals to diversify and eventually produce us. We might owe our existence to the Oort cloud in more ways than one. It may have delivered the water and organic molecules that made life possible, and it may have cleared away the dinosaurs that were blocking our evolutionary path. But I should be honest with you. the evidence is contested. A 2009 study from the University of Washington suggested that comet showers likely caused only minor extinctions, not the major events. The 26 to 30 million year periodicity is not universally accepted. Some statisticians argue it could be an artifact of incomplete data rather than a real signal, and separating asteroid impacts from comet impacts in the geological record is extremely difficult. Asteroids and comets leave similar craters. Both can trigger mass extinctions. Unless we can analyze the chemical composition of the impactor material preserved in the crater, we often cannot tell them apart. The Chicxulub impactor, the one that killed the dinosaurs, is now generally believed to have been a carbonaceous asteroid, not a comet. But the debate continued for years. Still, the possibility is sobering. The Oort Cloud is not just a distant curiosity. It is a reservoir of potential impactors, a population of objects that could, under the right circumstances, be redirected toward Earth. Consider the math. There are roughly 1 trillion objects in the Oort Cloud, larger than 1 kilometer in diameter. A 1 kilometer object hitting Earth at cometary speeds would be devastating. It would not cause a global extinction, but it would destroy a region the size of a country and trigger climate effects that could kill millions. Larger objects, the mountain-sized chunks of ice that occasionally appear as great comets, would be civilization-threatening or worse. And these objects are constantly being perturbed. Galactic tides are always operating. Stars pass by every few 100,000 years. Each perturbation sends a few more objects tumbling inward. Most miss Earth by huge margins. But over billions of years, impacts are inevitable. We are probably safe for the foreseeable future. The Gliese 710 encounter is 1.3 million years away. The current long-period comet flux is relatively normal, but on geological timescales, comet showers are a real phenomenon, and they have shaped the history of life on this planet. In some ways, we owe our existence to the Oort Cloud. Comet impacts may have delivered water and organic molecules to the early Earth, kickstarting the chemistry of life. But we also owe our vulnerability to it. The same reservoir that may have seeded life can also destroy it. Now let me talk about the structure of the Oort Cloud in more detail, because it is not uniform. There are actually 2 distinct regions. The outer Oort Cloud, sometimes called the classical Oort Cloud or the isotropic cloud, is the spherical shell that Oort originally proposed. It extends from roughly 20,000 to 100,000 astronomical units, maybe even 200,000. Objects here have orbits that are essentially random in orientation, coming from all directions relative to the plane of the planets. The outer cloud is where most long-period comets originate. It is the region most affected by galactic tides and passing stars. Objects here are so loosely bound to the Sun that even small perturbations can send them falling inward or escaping entirely into interstellar space. But there is also an inner Oort cloud, sometimes called the Hills Cloud, after astronomer Jack Hills, who proposed it in 1981. This region extends from roughly 2,000 to 20,000 astronomical units. The Hills Cloud is different from the outer cloud in important ways. It is denser, containing perhaps 5 times as many objects, and it retained more of its original structure. Instead of being perfectly spherical, It is somewhat flattened, like a thick disk. Objects here have orbits that are still somewhat aligned with the plane of the planets, though not as strongly as Kuiper Belt objects. A 2025 study revealed something fascinating about the inner Oort Cloud. It apparently has a spiral structure with two distinct arms, approximately 15,000 astronomical units in diameter and inclined about 30 degrees from the ecliptic plane. This structure is thought to be a relic of the formation process, a fossil of the gravitational sculpting that shaped this region billions of years ago. The Hills cloud matters because it serves as a reservoir for the outer cloud. Objects can be scattered outward from the Hills cloud into the classical Oort cloud over time, replenishing the outer population as objects are lost to interstellar space or sent into the inner solar system. Think of it like a fountain. The Hills cloud is the basin that catches water and recirculates it. The outer Oort cloud is the spray at the top, constantly losing material, but constantly being replenished from below. Let me talk about something that connects the Oort cloud to current research. Questions scientists are still trying to answer. You may have heard of Planet 9, the hypothetical large planet that some astronomers believe lurks in the outer solar system, far beyond Neptune. If it exists, Planet 9 would have a mass of maybe 5 to 10 Earths, an orbital period of 10,000, 20,000 years, and a distance that would place it in the inner Oort cloud region. The evidence for Planet 9 comes from the orbits of extreme trans-Neptunian objects, bodies like Sedna and 2012 VP113, that orbit at incredible distances with peculiar orbital alignments. Some researchers argue these alignments are best explained by the gravitational influence of an unseen planet. The hypothesis was formally proposed in 2016 by astronomers Konstantin Batygin and Michael Brown at Caltech. Brown, ironically, is the same astronomer whose discoveries led to Pluto being demoted from planetary status. He has joked that he is trying to give back the planet he took away. The proposed orbit of Planet 9 is extremely eccentric and highly inclined. It would spend most of its time far from the Sun at distances of 400 to 800 astronomical units, making it extremely difficult to detect. At those distances, even a planet several times the mass of Earth would be incredibly faint. Sedna is particularly interesting. It was discovered in 2003 by Brown and his colleagues, and its orbit is genuinely bizarre. Its closest approach to the Sun is 76 astronomical units. That is already way beyond Neptune and the Kuiper Belt. But its farthest distance from the Sun is 937 astronomical units. It takes 11,400 years to complete a single orbit. When Sedna was discovered, it was the reddest object in the solar system after Mars. Its surface is covered in organic compounds called tholins, complex reddish molecules created when ultraviolet radiation and cosmic rays bombard simple ices like methane and nitrogen. These tholins are believed to be similar to the organic compounds that existed on the early Earth before life emerged. Sedna is too distant to be significantly affected by Neptune's gravity. It is too close to be in the main Oort cloud. It exists in a kind of no man's land, the innermost fringe of the Hills cloud. How did it get there? Something must have put it there. Something with significant gravity. Several explanations have been proposed. Maybe a passing star in the Sun's birth cluster scattered Sedna outward. Maybe an undiscovered planet, like the hypothetical Planet 9, shepherded it into its current orbit. Maybe the Sun captured Sedna from another star entirely. We do not know. Since Sedna, other objects with similarly extreme orbits have been discovered. 2012, VP113 has a perihelion of 80 astronomical units, even more distant than Sedna's. Leleakuhonua, discovered in 2015, has an aphelion exceeding 2100 astronomical units, genuinely extending into inner Oort Cloud territory. These objects are collectively called sednoids. Each one we find tells us something about the gravitational environment in the outer solar system, and each one raises more questions than it answers. If Planet 9 exists, it would dramatically affect our understanding of the Oort Cloud. It would shepherd certain populations of objects. It would alter the inclination distribution of incoming comets. It would be the largest discovery in planetary science in over a century. But despite years of searching, no one has found it. The Vera Rubin Observatory, which began its decade-long sky survey in late 2025, is expected to either confirm or rule out Planet 9 within the next few years. If Planet 9 is out there, Rubin should see it. If Rubin does not find it after a few years of searching, the hypothesis will be in serious trouble. There is another possibility that some researchers have proposed, and it is even stranger than a hidden planet. What if Planet 9 is not a planet at all? What if it is a primordial black hole? A primordial black hole would be a tiny black hole left over from the Big Bang, with about 5 Earth masses compressed into a volume smaller than a baseball. Such an object would be almost impossible to detect directly. It would emit no light. It would be too small to see. The only way to find it would be through the occasional flares produced when it consumes small objects or interacts with dark matter. This is highly speculative. Most astronomers consider it unlikely, but it is not impossible, and it shows how much we still do not know about the outer solar system. Whether Planet 9 exists or not, the Oort Cloud almost certainly contains objects larger than typical comets. Sedna, at about 1,000 kilometers, is probably not the largest thing out there. Statistical models suggest there could be dozens of Pluto-sized objects in the outer solar system that we have not yet detected. Some might be lurking in the inner Oort Cloud right now, too far and too dark for our current telescopes to see. Every few years, someone proposes a new search strategy or a new survey that might find these hidden worlds. And slowly, one object at a time, we are mapping the outer solar system. Let me take you out there. Let me describe what it would actually be like to float in the Oort Cloud. You are surrounded by darkness, complete, absolute darkness. The nearest chunk of ice is tens of millions of kilometers away, invisible. There is nothing to see except stars. But wait, look over there. Do you see that one particularly bright star? The one that outshines everything else? That is the Sun. Counterintuitively, the Sun would still be easily visible from most of the Oort Cloud. At 50,000 astronomical units, it would have an apparent magnitude of about -3.3. That is roughly as bright as Venus appears from Earth. At 100,000 astronomical units, the outer edge of the cloud, it would still be brighter than Sirius, the brightest star in Earth's night sky. You would have no trouble picking out the sun, but it would look like a star, not a disk. There would be no warmth from it, no sense of illumination, just a brilliant pinprick in an ocean of darkness. The planets would be invisible. Even Jupiter, the largest planet in the solar system, would be far too dim to see with the naked eye from Oort Cloud distances. Earth would be completely undetectable. Everything you have ever known, every place humanity has ever lived, would be compressed into that single point of light, indistinguishable from any other star except for its brightness. The temperature around you would be about 4 to 5 Kelvin, negative 450 degrees Fahrenheit. You would die instantly, of course, but even if you were somehow protected, you would feel nothing, no warmth, no cold, just the void. At this temperature, almost nothing moves at the molecular level. Chemical reactions essentially stop. Time, in a chemical sense, stands still. This is why Oort Cloud objects are such perfect time capsules. The conditions out there preserve material unchanged for billions of years. Ice that formed when the solar system was young remains exactly as it was, waiting. And you would float there, alone, for eternity. Or at least, for the millions of years it would take to complete a single orbit around that distant pinprick of light. NASA describes it beautifully. Out in the Oort Cloud, objects coast along their orbits like lazy moths around a porch light. The light is there, but it gives no warmth. It offers no comfort. It is just a reminder that somewhere, impossibly far away, there is a star. Objects in the outer Oort Cloud move incredibly slowly relative to the Sun. An object at 50,000 astronomical units in a roughly circular orbit would travel at only about 130 meters per second, slower than a passenger airplane. At that speed, completing a single orbit takes over 11 million years. 11 million years. Think about that. The last time some Oort Cloud objects were in their current positions, the continents were in different places. The Mediterranean Sea did not exist. The Himalayan mountains were still rising. Human ancestors were small, tree-dwelling primates with no inkling of what they would become. And during all that time, those objects just drifted, slowly, imperceptibly, tracing their enormous orbits through the darkness. They will still be drifting long after humanity is gone, long after the sun itself has changed into something unrecognizable. And here is something that might unsettle you. You would not be alone in having a sun that looks like a star, because at Oort Cloud distances, you are getting close to other stars. Remember, Proxima Centauri is only 4.2 light-years away. The outer Oort Cloud extends up to about 1.5 to 3 light-years from the Sun. That means the Oort Cloud reaches somewhere between 1/3 and 3/4 of the way to the nearest star. And what if Proxima Centauri has its own Oort Cloud? We do not know for certain that it does. No one has ever detected an Oort Cloud around another star, despite searches going back to 1991. But there is no reason to think our Sun is special in this regard. If Proxima Centauri has a similar cloud extending 1 to 2 light-years from its surface, then the two clouds might overlap, or they might come very close. The solar system, it turns out, might not be as isolated as we thought. Our Oort Cloud might shake hands with the neighbor's Oort Cloud. Objects might drift back and forth between stellar systems, slowly, over millions of years, not quite belonging to either star. In roughly 30,000 years, Alpha Centauri will be only 2.9 light-years away, closer than it is now, because it is approaching us. At that distance, any Oort clouds around the Alpha Centauri system would almost certainly overlap with ours. We might share comets with our nearest neighbors without even knowing it. And this brings me to something remarkable that has happened in just the last few years. We have actually seen visitors from other star systems passing through our solar system. Not comets from our Oort cloud, objects from the Oort clouds of other stars. In October 2017, astronomers detected an object on a trajectory that could not have originated in our solar system. Its orbit was hyperbolic, meaning it was not gravitationally bound to the Sun. It came from somewhere else, passed through our inner solar system at incredible speed, and headed back out into interstellar space. They named it Oumuamua, a Hawaiian word meaning scout or messenger. It was the first confirmed interstellar object ever detected. Oumuamua was strange. It was shaped like a cigar or a disc, unlike any asteroid or comet we had ever seen. It was tumbling end over end as it flew, and it showed a slight, unexpected acceleration as it left the solar system, as if something were pushing it. Some scientists proposed that outgassing, the vaporization of ices on its surface, could explain the acceleration. Others suggested more exotic possibilities. For a brief moment, some researchers even suggested Oumuamua might be artificial, a piece of alien technology drifting through the galaxy. That idea was almost certainly wrong, but the fact that it was seriously considered shows how genuinely weird Oumuamua was. Oumuamua came from the direction of the constellation Lyra. It had been drifting through interstellar space for millions of years, maybe billions, before randomly passing through our solar system. It spent a few weeks within range of our telescopes and then vanished into the darkness, continuing its endless journey. We will never see it again. It is gone forever. But we did see another one. In August 2019, an amateur astronomer named Gennady Borisov discovered a comet with an even more clearly hyperbolic orbit. Comet Borisov, as it was named, was unambiguously interstellar. Unlike Oumuamua, it looked like a normal comet with a visible coma and tail. Comet Borisov was a refugee from another star's Oort Cloud. Billions of years ago, in some distant solar system, it formed from the same primordial ice and dust that made our own Oort Cloud objects. Then it was ejected, flung into interstellar space by the gravity of its home star's planets. It drifted for billions of years between the stars. And then, by pure chance, its path happened to intersect our solar system. We had a few months to study it as it passed. And then, it too disappeared, continuing its journey through the galaxy. These interstellar visitors tell us something important. The ejection process that created our Oort cloud happens around other stars too. Every star system probably loses billions of icy objects to interstellar space. The galaxy is full of these drifting, frozen refugees, wandering between the stars for eternity, and sometimes, by pure chance, they pass through. Astronomers estimate that there might be thousands of interstellar objects passing through our solar system at any given moment, most of them too small and dark to detect. Oumuamua and Borisov were just the first two large enough and close enough for us to notice. The Vera Rubin Observatory is expected to detect many more. Each one will be a messenger from another star, carrying information about conditions in distant solar systems billions of years ago. Let me give you some more scale comparisons before I wrap up, because these are the things that stick with you. These are the numbers that help your brain actually grasp what we are talking about. If you took a roll of toilet paper and let each sheet represent one astronomical unit, you would need about 50,000 to 100,000 sheets to reach the outer Oort cloud. That is roughly 5 to 10 miles of toilet paper unrolled in a straight line. You could lay it from one side of a small city to the other. Here is another way to think about it. Imagine the sun is a basketball sitting in the middle of a basketball court. At this scale, the Earth would be the size of a peppercorn, about 1 meter away from the basketball. Jupiter would be about the size of a grape, 5 meters away. Neptune would be 30 meters away, about the length of a basketball court. At this scale, where would the Oort cloud be? The inner edge would begin about 2 kilometers away. The outer edge would be somewhere between 50 and 100 kilometers away. You would need to drive for an hour on the highway to reach the outer boundary of our basketball solar system and the nearest star. At this scale, Proxima Centauri would be about 250 kilometers away, another 2 to 3 hour drive beyond the outer Oort cloud. If you could drive a car at highway speed, non-stop, 24 hours a day, it would take you 342,000 years to reach the inner edge of the actual Oort cloud, 8.5 million years to reach the outer edge. Longer than humans have existed as a species. Let me put that in perspective. Homo sapiens, anatomically modern humans, emerged about 300,000 years ago. 8.5 million years ago, our ancestors were not even close to human. They were early hominids, more ape than person. The evolutionary distance from those ancestors to us is shorter than the driving distance from Earth to the outer Oort cloud at highway speed. If you could travel at 1% the speed of light, vastly faster than any spacecraft we have ever built, you could reach the inner Oort cloud in about 10 years. But crossing the entire cloud would still take 250 to 500 years. Even at the speed of light, the fastest possible speed in the universe, it takes up to 18 months to cross the Oort cloud. A beam of light leaving the sun right now will not reach the outer boundary until the summer of 2027 at the earliest, more likely not until sometime in 2028 or beyond. Carl Sagan once noted that even with continuous 1g acceleration, the kind of acceleration that would feel like Earth's gravity pushing you into your seat, it would take about a year to reach the Oort cloud. A year of constant acceleration, reaching a significant fraction of the speed of light just to get there. The Oort cloud is so large that even science fiction struggles with it. Warp drives and hyperspace jumps are designed to cross interstellar distances, not to navigate the outer reaches of our own solar system. And yet, the Oort cloud is technically still part of our solar system. It belongs to our sun. Here is something that really drives it home for me. Voyager One, our most distant spacecraft, has been traveling for 47 years. It is moving at 38,000 miles per hour, and it has covered less than 0.2% of the distance to the outer Oort cloud, less than 1/500th of the way. If Voyager were a runner in a marathon, after 47 years of running, it would still be in the starting blocks. It would not have taken a single step. Let me talk about the future of Oort cloud exploration, because despite these daunting distances, we will learn much more in the coming decades. We cannot visit anytime soon. The distances are simply too vast, the travel times too long. But we can learn much more than we currently know, even from here. The Vera Rubin Observatory is going to be transformative. Located in Chile, it achieved first light in June 2025 and began its decade-long legacy survey of space and time later that year. Its 8.4-meter mirror and 3.2 billion pixel camera will image the entire visible sky every few nights for 10 years, building up an unprecedented database of moving objects. Rubin is expected to discover tens of thousands of new trans-Neptunian objects, including many sednoids orbiting in the inner Oort Cloud region. It will find new long-period comets years before they become visible to the naked eye, giving us more time to study them. It may find Planet 9 if it exists, or prove that it does not. Before Rubin, we knew of perhaps a few dozen objects with orbits extending beyond 500 astronomical units. Rubin could find hundreds or thousands. Each one is a data point. Each one tells us something about what lies in the darkness between the Kuiper Belt and the Oort Cloud proper. Every new object we discover at extreme distances tells us something about the Oort Cloud structure and population. We are building a statistical picture, object by object, of what lies at the edge of the solar system. There is also the possibility of detecting Oort Cloud objects indirectly through stellar occultations. When an Oort Cloud object passes in front of a distant star, it briefly blocks some of the starlight. These events are extremely rare and very short, lasting only fractions of a second, but they can reveal the size and distance of objects we could never see directly. Several surveys are specifically designed to detect these occultations. The Taiwanese American Occultation Survey and similar projects watch thousands of stars simultaneously, waiting for the brief flickers that indicate something has passed in front. Each detection is a tiny piece of evidence about the Oort Cloud's population. New space telescopes will also contribute. The James Webb Space Telescope, though primarily designed for observing distant galaxies and exoplanets, can study the composition of comet comas in unprecedented detail. Every long-period comet that passes through the inner solar system is an opportunity to analyze material from the Oort Cloud. The European Space Agency's Comet Interceptor mission, scheduled to launch in the late 2020s, is designed specifically to visit a pristine long-period comet or even an interstellar object. It will wait at a gravitationally stable point near Earth until a suitable target is discovered, then race to intercept it. This could give us our first close-up look at an Oort Cloud object that has never been altered by previous solar passes. In the more distant future, proposed missions could actually visit the outer solar system. NASA has studied concepts for interstellar precursor missions that would travel several hundred astronomical units from the Sun, reaching regions that might be considered the innermost fringes of the Oort Cloud. One concept, called the Interstellar Probe, would use a gravity assist from Jupiter and possibly a close pass by the Sun to achieve speeds of around 25 astronomical units per year. That is roughly 7 times faster than Voyager. Such a probe could reach 500 astronomical units within about 50 years of launch and could theoretically reach the inner Oort Cloud within a few centuries. Even reaching 500 astronomical units would be revolutionary. That region is essentially unexplored. We do not know what is there. We have theoretical models, but no direct observations. An interstellar probe would send back data from a part of the solar system that no human-made object has ever visited. Another concept uses solar sails, vast reflective sheets that catch the pressure of sunlight to accelerate a spacecraft without fuel. A solar sail deployed close to the sun could theoretically reach speeds of 5 to 10% the speed of light, fast enough to reach the Oort Cloud within decades rather than millennia. The Breakthrough Starshot project, funded by Russian billionaire Yuri Milner, is exploring an even more ambitious concept. Tiny spacecraft, weighing just grams, would be accelerated by ground-based lasers to 20% the speed of light. At that speed, they could reach the inner Oort Cloud in just a few years. These are ambitious proposals, and none have been funded for full development. But they represent real engineering concepts, not science fiction. The technology to reach the Oort Cloud within a human lifetime may be developed within the next century. The ultimate dream, of course, would be to send a probe to an actual Oort Cloud object, to land on one of those ancient icy bodies and analyze its composition directly, to touch material that has been frozen since before the Earth existed. Imagine drilling into the ice of an Oort Cloud object. Each layer would represent a different era in the solar system's history. The surface might show modifications from billions of years of cosmic ray bombardment. But deeper down, you would find pristine material, unchanged since the solar system was young. This is beyond our current capabilities, but it may not be beyond the capabilities of future generations. If humanity survives and continues to develop, if we master propulsion technologies that can achieve significant fractions of the speed of light, then someday a spacecraft might reach the Oort Cloud in a human lifetime. What would we find? Probably exactly what we expect. Ice and dust, frozen since the dawn of the solar system. But possibly something more. Complex organic molecules that might shed light on the origin of life. Isotope ratios that could tell us whether this object formed around our sun or was captured from another star. Structural features that reveal the conditions in the solar nebula 4.5 billion years ago. The Oort Cloud is a library written in ice. We cannot read it yet, but someday we might. Let me bring this back to Voyager One, because that little spacecraft is still out there, still transmitting, still carrying a piece of humanity into the unknown. Voyager One launched on September 5th, 1977, 16 days after its twin, Voyager 2. The mission was designed to take advantage of a rare alignment of the outer planets that occurs only once every 175 years. Jupiter, Saturn, Uranus, and Neptune would be positioned so that a spacecraft could use each planet's gravity to sling itself toward the next one. The original mission was planned to last 4 years. Study Jupiter and Saturn, send back photos and data, then shut down. Nobody expected Voyager to still be operational nearly 5 decades later. But here we are. Voyager One photographed Jupiter's Great Red Spot in unprecedented detail and discovered that it was a storm larger than Earth, swirling in the clouds for centuries or longer. It discovered active volcanoes on Io, the first volcanic activity ever observed beyond Earth. It revealed the intricate structure of Saturn's rings, showing that what appeared from Earth to be a few broad bands were actually thousands of individual ringlets. It discovered new moons. It found evidence of nitrogen geysers on Triton. It rewrote the textbooks about the outer solar system. And then, instead of shutting down, it just kept going. In 2012, Voyager One crossed the heliopause and entered interstellar space. The news coverage said it had left the solar system, but you know now, that was not quite true. Voyager has left the sun's magnetic bubble. Yes, it is no longer surrounded by the solar wind, but it has not left the sun's gravitational influence, not even close. Voyager 1 is currently about 167 astronomical units from the sun. On November 13th, 2026, it will reach 1 light day from Earth, the first human-made object ever to achieve that milestone. But the inner edge of the Oort Cloud is at least 2,000 astronomical units away. Voyager is still in the solar system's front yard. It has not even reached the sidewalk yet, but it is on its way. Every day, Voyager moves about 1.5 million kilometers farther from the sun. Its signal is incredibly faint now, about 23 watts when transmitted, roughly the power of a refrigerator light bulb. By the time that signal reaches Earth, it has spread so thin that the received power is measured in billionths of a billionth of a watt. But we can still hear it, barely, and Voyager can still hear us. The round-trip communication time is currently about 46 hours. Voyager sends data, and we do not receive it until nearly 2 days later. We send commands, and Voyager does not receive them until nearly 2 days after that. The Deep Space Network, a collection of massive radio antennas spread across California, Spain, and Australia, maintains contact with Voyager. These antennas are so sensitive that they can detect signals that have crossed billions of kilometers of empty space, signals that have been diluted by the inverse square law until they are barely distinguishable from the cosmic background noise. But Voyager will not last much longer. Its radioisotope thermoelectric generators are decaying. The plutonium inside them is slowly breaking down, producing less and less heat, generating less and less electricity. By 2030 or so, there will not be enough power to run any instruments. By 2036 or so, there will not be enough power to run the transmitter. Voyager 1 will go silent. It will keep drifting outward, carried by its own momentum, but it will no longer talk to us. It will become a ghost, and then, in about 300 years, that ghost will reach the inner edge of the Oort Cloud. There is something poetic about that. Voyager will spend 3 centuries crossing the relatively empty space between the heliopause and the Oort Cloud, a region we have barely explored. And then it will spend 30,000 years crossing the cloud itself, surrounded by 1 trillion objects it will never see and never approach. In 40,000 years, Voyager 1 will pass within 1.6 light years of a star called Gliese 445 in the constellation Camelopardalis. It will not stop. It will not even slow down significantly. It will drift past, carrying its message from a species that may no longer exist. On Voyager 1, there is a golden record. It was designed by a committee led by Carl Sagan, who understood that Voyager would eventually travel far beyond any chance of retrieval. He wanted to send a message in a bottle, just in case someone, someday, somewhere, found it. The record contains sounds and images from Earth, greetings in 55 languages, from ancient Sumerian to modern Wu Chinese, music from around the world, Bach and Beethoven and Chuck Berry, and traditional songs from dozens of cultures. The sounds of wind and rain and waves, a mother kissing her child, the brain waves of a woman in love. There are photographs encoded on the record, pictures of humans, of animals, of landscapes, a diagram showing where Earth is located in the galaxy, instructions written in a universal language of physics and mathematics, explaining how to play the record. The committee debated what to include. They wanted to show the best of humanity, to present our species as curious and creative and capable of love. They chose not to include images of war or suffering or death, although some argued that such images would be dishonest. In the end, the Golden Record is a curated message, a hopeful message, a message that says, we existed, we wondered, we dreamed of reaching the stars. That record will survive for billions of years, long after humanity is gone, long after the sun has exhausted its fuel and expanded into a red giant, long after the Earth itself has been destroyed. The Golden Record will still be out there, drifting through the darkness, carrying the faint echo of a species that once looked up at the stars and wondered. The Oort Cloud is humbling. That is the first thing it teaches us. Humility about the scale of things. We look at the planets and think we understand the solar system. We send probes to Mars and feel like explorers. And then we remember that everything we have ever visited exists within the innermost 1% of the sun's domain. Think about what that means. Every crater on the moon that astronauts have walked around, every canyon on Mars that our rovers have photographed, every ring of Saturn that Cassini flew through, every moon of Jupiter and Uranus and Neptune. All of it exists in a tiny bubble at the center of the solar system. The Oort Cloud surrounds all of it, the way the ocean surrounds a single grain of sand on a beach. We think of ourselves as space explorers, and in a sense, we are. We have sent machines to every planet. We have landed on asteroids and comets. We have reached interstellar space, or at least the space beyond the solar wind. But we have not come close to the edge of our own cosmic neighborhood. We have not even come close to coming close. The Oort Cloud is ancient. Objects there have remained essentially unchanged for 4.5 billion years. They predate the evolution of life on Earth. They predate the formation of Earth itself. When those objects settled into their distant orbits, the sun was young, the planets were still forming, and the solar system was a place of violence and chaos. Those chunks of ice were there when the first single-celled organisms emerged on Earth. They were there when fish first crawled onto land. They were there when dinosaurs ruled the planet and when an asteroid ended their reign. They were there when the first humans looked up at the sky and wondered what those wandering stars might be. And they will be there long after we are gone. Whatever happens to humanity, whether we spread to the stars or destroy ourselves tomorrow, the Oort Cloud will continue its slow drift around the sun. Objects that are out there right now will still be out there in 1 billion years, essentially unchanged, still waiting. The Oort Cloud is connected to us. The water in your body, the carbon in your cells, may have been delivered to Earth by comets. The extinction events that shaped evolution may have been triggered by Oort Cloud objects sent inward by passing stars. We are not separate from this distant cloud. We are influenced by it, shaped by it, possibly born from materials it contains. Every atom in your body was forged in stars that died before our sun was born. Some of those atoms may have spent millions of years drifting through interstellar space before being captured by the solar nebula. Some may have been part of an Oort Cloud object once, before being delivered to Earth by a comet impact 4 billion years ago. You are made of star stuff, but you may also be made of comet stuff. The line between us and the Oort Cloud is not as clear as we might think, and the Oort Cloud is vast, inconceivably, incomprehensibly vast. A structure so large that light takes 18 months to cross it. A structure so large that our fastest spacecraft will need 30,000 years to traverse it. A structure that stretches almost to the nearest stars, defining the ultimate boundary of our cosmic neighborhood. We live inside this structure. Right now, as you read these words, you are surrounded by the Oort Cloud. It extends in every direction from the sun, forming a sphere that contains everything you have ever known. It is not out there somewhere. It is here. We are inside it. This is the true scale of the solar system. Not the neat diagram with 8 planets orbiting a yellow star. Not the textbook illustration that fits on a single page, but a vast, dark, cold shell of ancient ice stretching nearly halfway to the nearest star, containing more objects than there are grains of sand on all the beaches of Earth. The Oort Cloud is out there right now. It has always been there, silent and immense. It was there before humans existed. It will be there long after we are gone. It surrounds everything we have ever known, everything we have ever explored, everything we have ever called home, and we have only just begun to understand it. Voyager One continues its journey. Every second, it moves another 17 kilometers farther from Earth. Every hour, it travels a bit more than the distance from Earth to the Moon. Every year, it puts another 3.5 astronomical units between itself and the Sun. In 300 years, it will arrive at the inner edge of the Oort Cloud. In 30,000 years, it will exit the other side. Whatever happens to humanity in the coming millennia, Voyager will be there, moving outward, crossing the cloud, carrying our voice into eternity. The Oort Cloud is the solar system's final frontier, the edge of everything we belong to, the boundary between our sun's family and the wider universe. It is there, right now, surrounding us, a trillion frozen worlds waiting in the darkness, and every once in a while, it sends us a message, a comet streaking across the sky, a visitor from the edge of forever, carrying ice that formed before the Earth existed. Look up the next time you see one. Think about where it came from. Think about how long it waited. Think about the journey it made, falling for millions of years from the outer darkness. Think about the trillion other objects still out there, still waiting, still drifting in their ancient orbits. Think about the vast, cold, ancient structure that released it after billions of years. That is the Oort Cloud. That is the true scale of where we live.